Hello everybody, it is Sam the Reclaimer developer, and I am finally getting to the video that I said I was going to do for a long time, and it's the video on the Reclaimer's entity system. And as you can probably tell by the title of the video, it's not really something I consider to be like an extremely important part because uh, this way of thinking about data has been around for a really long time, and it's like people are rediscovering it and just being like, look at this brand new, you know, galaxy brain way of thinking about data. And I'll be honest, when I discovered or when I learned about the concept of entity component systems, I was like, wow, this is a really cool concept. But then I learned, like, this is just knowledge that has been lost to uh, modern computing, with, like, everything being, you know, abstracted and put into this philosophy of, like, clean code and how nothing can be done uh, without virtual functions and inheritance and things like that. Well, uh, I mentioned it in a previous video, but Jonathan Blow, he's the developer behind The Witness and Braid, and he said it best when he said entity systems are not the important part of a game. It's like, yeah, they're a part of the game's architecture, but no one is going to care what type of entity system that you use, whether it's something that's object oriented, like inheritance based or composition based, or, you know, what have you, because the interesting problems are ones that keep your players engaged and coming back to play your game. And I was like, that's kind of a really deep way of thinking. And also, I don't know why Microsoft Whiteboard insists on having an internet connection in order to function. I don't know if there's a setting I can turn off for it, but I'm about done with this stupid program. Aside from that, let's talk a little bit about entity systems. So you can have, in, like, the more traditional object oriented way of thinking about things, and I'm going over stuff that, like, if you're a seasoned programmer, you know the stuff already. But, like, let's say you have a base thing in, you know, like, a typical object oriented way, and I'm not knocking on, you know, object oriented programming in and of itself, but I'm just I'm just highlighting some key differences. So, like, you may have some type of interface or abstract object that has, you know, maybe a few functions. Like, a core thing in every entity is going to be like an update, right? Every entity has to have a way of knowing when it needs to update its members, right? And so that could be like some type of abstract class. And then let's say you have more objects that, you know, you inherit from, like, I don't know, let's say player character, right? So it inherits from I entity, so you know it's going to have an update function, right? Just right off the rip. So we have this class player, and it might inherit from some other things, like it's I don't know, a physics object, which basically means it's going to have a position and a velocity and some other function that maybe get called. And let's say it's a renderable. So it's just these things about, you know, the programmer can reason about, like, the behaviors that it wants the player class to inherit, right? And again, I'm not knocking on object-oriented programming. This is just like a typical, like, what you would see in more of a traditional, like, object-oriented way of doing things. So And so, like, let's take a look at what we've got. So, like, these members, we know we're going to have, because of our physics and our renderable, like, let's talk about, we're going to have a position, which may have, like, it's going to have an X and Y. And then we're going to have a velocity, which also is going to have, like, X and Y. So it's like the position is the coordinates, and the velocity is like the direction, right? The direction and the magnitude and everything like that. So it's like we have, we can reason about like movement vectors and stuff like that. And then with the renderable, like we might have something that the GPU is going to use, like, we may have some type of mesh, or let's say, I don't know, like an OpenGL, like vertex array objects, and maybe some type of reference to a shader, something that is going to be bound to whatever rendering context is active, so that we know what we need to tell the GPU in order to render it. And then there's going to be methods that is going to be updating everything, right? So we have like a core update, which is going to have like our custom like iEntity update things, and there's going to be like an update position, or this could be like a base function, right? That is going to be tied to, the physics object. So like every frame, anything that inherits from physics is going to be updating the position, velocity, things like that. And the renderable, there may be some type of like render that is inherited from the renderable. And these things may be not entirely visible. Like these are things that are sort of obfuscated in the physics and renderable classes. It's like implied that they're going to be called every frame, right? And you have, somewhere in the game there's going to be a like a list of entities, right? And so there may be some type of collection that can be dynamically updated that is going to store all of our entities, and then, wherever that is located, somewhere else down the line, there's going to be like a for each, entity in entities, there's going to be some call to entity dot update. And, this is sort of a very high-level overview of how, typical object-oriented things might work. And, like, this isn't, like, specific, in every engine/game is going to have their different way of doing things. But this is just sort of a typical, like, inheritance hierarchy, right? So let's go ahead and go down a little bit. And so you could have, you've got your core entity, and then you have other subclasses, right? You've got, like, human, and you may have, like, orc, and you have classes, like, subclasses of human, like, you can have, like, a wizard, and you have a, cleric, and then, like, maybe subclasses of orc could be, like, barbarian or something. And so you may run into this typical problem, and again, it's kind of exhausting going through this, because it's like everybody has people who are a lot more adept at this stuff than I am can explain this stuff better, but it's like you run into this problem where it's like, what if you want to do something like this, right? So there's not really a clear path, or at least a sane path, that allows you to do these different types of things, and you have to do this like multiple inheritance type structure where you have like because of this weird thing inside the human class, or you may have to do this weird thing where you have to put in a reference to an orc class in order to access the barbarian or something like that. But it's like implied that if you find a way to get this working with human, you're going to have some type of reference to this, and it can just be kind of a mess depending on what it is that you want to do. And it's not that this case is always bad, because it's like, design your entity system around, it's like, what is it that you're trying to accomplish? Well, I don't really subscribe to this method. It is certainly a way I used to think about things back in the day, but let me grab this book that I want to talk about. And this is not me wanting to go through like a lesson on this book, but it's called Data-Oriented Design by Richard Fabian, Software Engineering for Limited Resources and Short Schedules. And the thing that it talks about very early on is, think of your data like in terms of like how you would structure a database, right? So let's talk about databases really quick. So, databases are essentially, you have tables. You have maybe like table 1, and you have table 2. And there will be like records in there that store some things, and table here that stores some things. And so what would that look like in terms of, what we were looking at up here, and specifically these things down here? An entity system, entity component system would, of course, call these components, and it's what I'm calling them as well, because I'm thinking of entities in the Reclaimer as composition based. And so what I mean by that is, I want to be able to choose sort of on the fly what I want an entity to be composed of. And there's sort of this proof that the book goes through, that you can describe entities based on the components that they contain. So like when you start thinking of data containment, these complex objects are really just a signature based on what data that they contain. So, and I think the first step in that is thinking in terms of databases. So, or at least, thinking in terms of data tables. And so what that would mean is, like, if you remember, we had, like, our components up here. You would have a position table. And, of course, it would be defined by x, like, let's call it x coord, because that's what these are. They're coordinates, right? So, like, x coord and y coord. Let's pretend in this world where this entity system exists, it's two-dimensional, not 3D, so I don't have to write so much. And you would have a velocity table, which of course would have like x velocity and y velocity. And you would go on to have, let's say, a rendering table. And let's keep this simple. So, like, you would have, like, in terms of, like, OpenGL, you would have, like, maybe a VAO that it binds, and, I don't know, let's say, num vertices. Let's just assume it's, like, really simple. We're not doing index-based rendering. We just take a collection of vertices that are part of a buffer that are bound to a vertex array object. And there's two systems that these are going to be using. So, like, one, you've got the rendering, which is essentially going to loop through all of the rendering, all of the entities in the rendering table, and then you have like a physics table or a physics system that is going to take in these two, and there's going to be a loop that takes the velocities of the objects and updates their position. So, seems simple enough. And so, that's sort of what I'm doing in the Reclaimer. So, I create an entity, which is another way of saying it's an ID, or more specifically, an index. An entity is an index. And it corresponds, the index corresponds to those data tables. So every table has the same number of elements, so that no matter how many entities I have, there's always room for updating certain elements in that table for that entity. And so when the game starts up, I have a collection of components that I want the game to have. So what I do is I determine a number of entities, and for how many components I have. So in this really simple one, I have position, velocity, and rendering. Let's say in this world, I'm going to have a maximum of like 255 entities. And I'm not saying this is how the game is going to be released. I'm just saying, like, this is what I'm doing currently. So each one is going to be 255, 255, and I should probably say like 256 really, but who cares? We'll just go with 255. And so that's going to be the count. Every position, like the position table, is going to be allocated to 255 elements. Velocity is going to be allocated to 255 elements. And so so that way, let's say if I create an entity and its index is 5, I will know for certain that when I want to update a position at index 5, there will be something there. I never have to worry about allocation because everything is done up front. And I know the system isn't perfect, but what it does is it gets us away from this idea that entities are based upon what they are. Instead, it's based around what an entity has, if that makes sense. So we moved away from data like relationships, as in an entity is a thing or is not a thing, and instead we think of entities as has a thing instead of being is a thing. So instead of an entity having an orc or having a barbarian, it's like reverse of that. So instead of an entity being like it is an orc or it is a human, it's like it has a human component or it has a orc component. And so now you do this thing of like, I can create an entity that has a human and has an orc component. And now I've just created a half-orc, right? So all I have to do is just create a new query. Because remember, we're talking about tables. And so that means queries. And I say queries, but it's more or less just like looking for, like, when we loop through all the entities, we can just index certain components at those indexes and just be like, do you have this and this at the same time? right? So if I want to update a position, I'm like, it must have a position and it must have a velocity at the same time. And if they do, we update them. And I don't really like to think in terms of like systems. I may use the word system interchangeably, but I don't want to force a certain paradigm into the reclaimer, that because thinking in that way is, in my opinion, no better than like forcing yourself to conform to like the object oriented like inheritance type structure. Because in my view, it's whatever gets the job done. If you choose to subscribe to the sort of like inheritance based hierarchy and that works for you, great job. And same goes for entity component systems. If the ECS way of thinking about things gets the job done for you, again, that's more power to you. I'm happy for you. But how I choose to do things is I just don't want to force a certain way of thinking about things, because data is data, and it's whatever gets the job done fast and efficient. And sometimes that may mean subscribing to something that doesn't always work for every case. And the only thing that I'm worried about in terms of this structure is information density. Right? So you can imagine you can have this like massive structure. So like if you were to put all of the memory together, and that's essentially what I do when I initialize the game. There's a huge chunk of memory, and for this particular example, when the reclaimer starts up, I request 1 gigabyte of data for the entity system. And so as I define components, it uses up that 1 gigabyte partition, right? So the entity system has this big chunk of data that will say from 0 to 1 plus billion bytes. I define the position, and remember, it's based on the max number of entities that I allow the system to have. So there's the position table, there's the velocity table, and this is not to scale, by the way, and the rendering table. So it's whatever to allocate the position is like, of course, size of position times 255. And so that's what the table definition looks like. I just say, hey, starting at the, first available pointer. So it kind of allocates like a stack. It's very linear that when the game starts, all of these components are going to be defined, and the memory is just there for the duration of the runtime of the game. Like, it never changes. Things are not dynamically allocated. And wherever this starts, like, let's say this is the beginning position. So the ID of the component in terms of like where it's located in the memory space is that index. And its address is going to be this. Like, this is the address. And so the address of the velocity table is going to be this one at the end of the position, right? And so the rendering address is going to be at the end of the velocity table. So on and so forth. And so what I've done is I create this thing called a sparse array. And like, this isn't new. This is something that I've just adopted. So the type is literally just indexing through these things, right? So I've got 3 different components And so it's 0, 1, and 2. And those are the IDs, and their addresses are whatever their address is in that table, whatever their index is. And so you have a component, like the generic signature of a component. It has an ID, and it has an address to wherever it is in that table. And so it's like you have these indexes, or rather, you have the type, which is dense, which indexes just like based on whichever type, right? And so this is dense. And then the actual address is sparse, right? So it'll be wherever that resides in the table, like its actual index in that big 2 gigabyte buffer, right? And so that brings us to the problem of information density. So you've got this big ass table. Big ass table. Cannot spell. And so you've got your position partition. You've got your velocity partition. And you've got your rendering partition. Right? And so all of this is, just open space. And so this is me like addressing like the problems that I see with this. So these partitions are just going to be filled with stuff that may or may not be adjacent to each other, right? And so in the position table, or I'm sorry, the velocity table, let's say, for example, this entity right here has both a position and a velocity component. So I can confidently grab this guy right here knowing that it has a position and a velocity component. Well, I know that the velocity pretty much isn't going to exist without a position. So like something without, a manifestation in space can't really have a speed, can it? But things that are manifested in space may not have a velocity. And so an example of that would be static objects. For instance, in the game, there's going to be walls, right, that you can't move. When you run into them, they stay static. And so that may look something like this. And so that's an entity, this is an entity, that's an entity, that's an entity. So we could say something like this entity right here is the player, and he's being chased by an enemy, and the player is hiding behind this wall, right? So what you can see is there's this like hole here, right? And so the player and the enemy would be taken up by the same systems, as in like, update these dynamic entities that have that are superficially related, right? So, but it's going to skip over this because the system that looks at entities with position and velocity at the same time is going to skip that over. And of course you can store entities together. Like the physics library could just store like, hey, when I see that something gets created with both of these components, I'm just going to store those and then index them. But we still run into the same problem of we have like a dense array of things and like a sparse array of things, and the information density is low. And and what I mean by information density is exactly that. You have all of this empty space. And I'm just like doing these silly clouds to show that things aren't together. And so what that could potentially mean is it's not as cache friendly as you think, right? Because everything's sparse. It's going to be jumping to here and then jumping to here and then jumping to here. So, and I could be wrong, but this to me says very low information density. And a good example of that is booleans and structs, right? So a boolean is going to be like 1 byte. And how much information do you get out of a boolean? Like, it's going to be 1 byte regardless. But a boolean only has 1 value, which is true or false. And so that means you've got 1, 2, 3, 4, 5, 6, 7, and then our 8th bit is going to be what we actually look for. So this is the value, and this right here is just waste, right? It's just noise. It's stuff that has to exist because we need to get this one value. And so imagine, let's say if I have a array, a bool array that is 10 wide. So multiply this by 10. So we've got like 8 times 10 is 80, with only 1 times 10 value, right? So just 10 bytes. That's ridiculously low information density. So by far, most of that is just noise. It's just waste. So, and a good example of that is how things are done in the user input of the reclaimer. And I'll finally get away from the whiteboard and start looking at code. So let me go ahead and switch over to my primary screen. And I'll go ahead and pull up the user input. So we can think about key codes and key presses in terms of like, this is Win32 user input. I want to go to like reclaimer user input, right? So like these are all like the reclaimer's key codes. And, you know, a button being pressed down or released can be represented as a Boolean, right? It's 1 bit of value. But what is kind of sucks about that is I would have to store a byte for like 100 and some change statuses, 100 and some change buttons. That's very low information density. So what I do is I say, let's compress all of that data into, we have a certain number of button states that we need. And each one of them only has 1 bit of value. So let's say we take the number of buttons and put those into a single array. Let's group them together, right? Let's put them in groups of like bytes. So instead of 1 byte being associated with 1 key, we say the bits in a byte are associated with a bunch of different keys. So like 1 bit to like F1, 1 bit to F2, 1 bit to F3. And so these groups are put together in an array. And so there are 112 key codes, and each key code is represented by a bit. We store the data in a space created by 14 bytes instead of 112 bytes. So that's a pretty significant use of information density. And so that brings me to, like, let's circle back to entity systems and what they essentially are. All of this is to say, oops, I do not like the whiteboard program. Entity systems, whether they are inheritance-based or composition-based, are both representations of the same thing, and that is compression. Entity systems are compression algorithms. It's as simple as that. So when you think about it like that, it's just a way of trying to raise the information density of whatever components that you're working with. It's trying to structure things in such a way that they take up as little memory as possible. And that's essentially how I'm trying to think of things in the Reclaimer. Is I'm trying to use my memory as efficiently as possible. And I do that in whatever way works best. But I recognize that this big-ass table way of doing things may not be as good for information density. And I'm already violating one of my rules in that there's a Boolean that's stored in the, I think it was like the Reclaimer entity system types, I think. Was it? Yeah, the entity store. Yeah, there's an array of active entities, and this was just kind of to get things working. And I just realized that I'm not looking at the right screen. So we'll be over here looking at the code for the rest of the video. And I'm sorry that this video is a bit long-winded. But it essentially just stores the active entities, and I think each entity stores an array of component types that helps me determine, it's like, which does an entity have a certain type associated with it. So that's essentially it. And so this is like the entity system in a nutshell. So we have component types, which is essentially just an index. It's an ID, and the component index just tells us where things are in that table. And I do apologize if I'm getting things a little mixed up. It's been a while since I originally put this together. But essentially, the core thing to take away from it is that it essentially works like a database, kinda. It's just this memory space that is indexed that tells me where all of my components live. And like if I were to allocate a table, it finds the next free index in that big buffer, and its table is located right there. That's the component type. And so how do I define a component? It's like, this is essentially it. What is its index? What's its type? And there's the data. So we have the component store, which is the maximum amount of types, and currently it's only 256. This is very low for like the scope of the game, but this is just to get started and to help me visualize patterns of how things can be compressed. So what are the max types? And we have entities that are essentially just a collection of these IDs. And the entity ID is an index in a component table that helps me get the data. That's pretty much it. And then we have the entity system state, which just contains the entity store and the component store. It doesn't get too much simpler. And there's tons of like libraries out there like Flex and NTT, like ENTT, that are, I've looked through the source code and it's a little bit more complex than what I need. And I understand that this is probably a naive way of doing things. It was just something to get off the ground, and there's always a better way of doing things. Entity systems to me are interesting, but I know it's not going to be the thing that brings players back and what makes the game interesting. Because it's like, at the end of the day, nobody is going to care. It's like the entity system is a tool. It is a tool that I use to build the interesting parts of the game. And so if I were to go to like Reclaimer rendering components, actually, let me go to the physics library, because I mentioned that there was a new physics library, and it just stored really simple components. So we have the components type that the physics library exposes are the position, the velocity, and the rotation. And so these are easy things that we can reason about. It's like, what's the position in three-dimensional space? Which direction is it moving in? And what's its orientation, right? And so I just defined these tables. When I go to the physics components, like initialization, I just say physics components. We just say to the entity system, I want to define a table for positions, I want to define a table for velocity, and a table for rotation. And for each one, we just take those and put them into this table over here so that we can have an easy way to reference them. And then we just have some helper macros and functions to either update or read data. And that's pretty much it. It doesn't get any more simpler than that. And let's, like, if I go to physics, I think it's physics systems, we can see an example for how we update positions and transforms. So this is a very, very simple function. We get the entity store, so we have access to all the entity indexes. We grab the position table, the velocity table, and then we just update the position by the velocity. And I keep shrugging a lot because while it's interesting to see the performance benefits of this sort of like composition-based architecture, at the end of the day, it's simply compression algorithms. And it's trying to visualize your data and see patterns in such a way that it's like, hey, I can probably like raise the information density, increase the ability to cache things, and make the system perform better. And again, this is probably like a naive way of doing things, but this is how I've chosen to start. And then hopefully this way of doing things, what it does is it reveals patterns. Whereas the typical like object-oriented approach can obfuscate patterns. Casey Muratori did a recent video on clean code, horrible performance, and that was one of his points. And I was like, that's really cool. I'm going to steal that and use it in when I talk about entity systems. And that's sort of what my goal is with this entity system, is can I reveal patterns about how data is structured so that I can continue to compress it and increase the performance and make the use of the memory that I've allocated. So I know this video's been a bit long-winded. It's another friggin' talk about stupid entity systems. But thanks for sticking around, and I will see you in the next video.